that?
He said he thinks he's getting a flu.
Yeah.
Oh,
Yeah.
well, get out of here.
Right. Yeah.
Watch the video.
You're gonna stay while the flu.
Thanks for
Sounds
that.
like you. Skip some
Thanks for
class.
that information.
All right. So, the solution of the continuous least squares problem of find Pn where these are polynomials. Such that the 2 norm of the error between f and Pn is at a minimum is given by these coefficients, the inner product. This is just a recap of last time. As a ratio of these inner products, just to refresh your memory, this is our inner product. And our norm. Okay, so that is the solution if these functions that span your space of polynomials of degree up to n are orthogonal, meaning that inner product of Phi and Pj equals 0 if I not equal to j. Okay. So the question for today is how to get orthogonal polynomials. Okay. Now, so what we can do is, so that I'm not going to get very general, to orthogonalize any set of vectors. So these could be any inner product space whatsoever. So these vectors could be vectors in Rn, or it could be functions, doesn't matter. So these are your original vectors, A1, A2, up to AN. And the only requirement on these vectors is that they be linearly independent. To produce new vectors, P1, P2, up to Pn, where these are orthogonal. You can use this algorithm, which you may have seen before. Gram-Schmidt Orthogonalization. Okay. And this is one of those algorithms that, although it's a simple enough algorithm that you can teach to undergrads, and maybe it is taught in a class like 426, but one problem is that, of course, undergrads think it's so funny to call it Gram-Schmidt.
Really? No. Do they actually do that?
Well, when I learned this as an undergrad, yeah.
Oh.
Yeah, I don't know if students here do, or if this is even taught in that class, but like, well, you took that class. Did it come up there?
Possibly. I mean, there's lip
Oh.
shits, that's even worse.
You just took a comprehensive exam on this. It did? Okay. All right. Yeah, but that's a problem too. lip shits.
That's terrible, that's a terrible last name.
Yeah. Well, then.
Sounds like something you got. You don't shut up.
Well, I had a professor named Lipschitz, but it just spells slightly differently than the Lipschitz from Lipschitz continuity, because one has a C and the other doesn't. But then he became department head, so I was like,
I know someone with the last name of Butts. Like, I'm not even kidding.
Oh,
Their
I
last
know
name is
somebody with last name Butts.
That's really.
oh, we have a Professor Butts here at USM. So yeah.
I couldn't do it.
Yeah, I'm one of the few professors I'm Facebook friends with. So
Oh.
yeah. In fact,
We should have Michael.
yeah. In fact, she's chair of graduate council now. So, okay. So, what is Gram-Schmidt orthogonalization? What?
I bet you got some New Girls TV show. There's a guy on there named Schmidt, and I just realized that. Yeah.
Okay. You have to start with this list of linearly independent vectors, and then did you ask what the Gram-Schmidt?
What? Sorry.
You asked a minute ago what he's looking at me like I'm crazy. You asked what it was. I'm just answering for you.
No, I didn't. I wasn't actually asking.
Oh,
I'm about to tell you.
Okay, you can tell me.
Or you can tell me.
No, that's okay.
You can tell the class.
I told Dr. Horner the other day on that.
Okay. Oh God, I'm not gonna get from this class. So, what? Okay, everybody stop. So what you do is you set your first orthogonal vector is equal to the first input vector. So we're off to a roaring start. And then your next vector, P2, has to be, you start with A2, but you have to make sure that P2 is orthogonal to P1. So you subtract something off to make that happen. And that's accomplished by doing this, so inner product. So for whatever inner product you have for that vector space, so that's this. So this is just going to be a number times P1. And so I'm going to work out for this case, showing you why that guarantees that P2 is orthogonal to P1. Because now if I take the inner product of both sides of this equation, which is something that's important for you guys to be able to do anyways, just like you do many things to both sides of an equation, taking inner products of something is important too. So I take, and using the fact that the inner product is linear, so this ratio of inner products, those are just numbers, so that doesn't change. But now this P1 has its inner product taken with itself, and now you have these inner products of P1 of itself canceling out, and the inner product is commutative, so it turns out to be 0. So it works out beautifully. Now you can keep going. So for instance, P3 starts out to be A3, but now I have to orthogonalize it against P1 and P2. So to orthogonalize against P1, it's going to be pretty much the same thing, except instead of A2, I have A3. And then times P1. And so that'll take care of that orthogonalization. But now I also have to orthogonalize against P2. So the further you go, the more work you have to do, unfortunately. So computationally, it's a rather expensive process. So in general, So each pj is equal to aj minus the sum all right, so then I have inner product of pk with aj over pk with itself times pk. So I'm taking aj and I'm orthogonalizing it against all previously computed p's. And that's the whole Gram-Schmidt algorithm. So in fact, if I just say, so this is true for j equal to 1, 2, up to n. So this in a loop is the whole algorithm right here. Okay. Now, so this gives you orthogonal vectors. If you want orthonormal vectors, then all you have to do is define like qj to be equal to each pj divided by its norm. Where this is, okay, so this is a 2 norm. So square root of inner product itself, or whatever inner product that is, whether it's like the dot product of vectors in Rn or the integral that I gave earlier. No loop. So this works for any inner product space. All right. All right. So questions about this process? So in fact, in 610, we're going to revisit this, but about for numerical linear algebra, doing this with ordinary vectors, and I'll show you why numerically it's actually terribly awful, this algorithm in terms of round-off error and stuff. But for our theoretical purposes, it's beautiful. So context is
I
it.
remember this in 610.
What?
I think I remember you teaching this in 610.
I would have, yeah.
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 I mean, I know that's what you just said, but
Yes.
that's where I remember it from.
Yeah.
So.
Yeah, it's awful. So, yeah, theoretically beautiful, numerically awful. Okay.
Does it store the values, or do you have to actually compute like every single one every single time? That sounds terrible.
Of these inner products, you mean?
Yeah.
Well, things every single one of these inner products are different. So
because it's with the A value.
right, yeah, because these k's are being reused, but always with a different a.
Yeah.
Yeah. So in fact, you're going to have 1, 2, 3, 4, up to n minus 1 of these all stored. Well, in fact, this is related to the QR factorization. So where A are your original A vectors as columns, Q would be these normalized vectors, and these, and then the entries of R would come from the inner products. And because you have 1, then 2, then 3, R is an upper triangular matrix, but it's still, that half of it is still full. So yeah, it is a lot of work. It's for n vectors.
Well, because I was thinking on the bottom, you're going to compute that, like you would compute P1, the inner product of P1 J times. Because you'd have to compute it for every single,
Yes.
or J minus 1 times. So,
Yeah, so for vectors in Rn, it takes order n cubed operations. So yeah, we don't want to do that unless, yeah. Now, yeah, this is actually using KSS methods, but yeah, it's 2 vectors, so who cares? Okay, now, so now for polynomials, I'm going to adapt this a little bit. because things become unexpectedly simpler in a polynomial case. Whoops. Schmidt it.
Oh, you s-
Okay, so what you do is, I can do this in like an inductive fashion. So we assume that polynomials p0 of x, p1 of x, p2 of x, and so on, all the way up to pj minus 1 of x. So your first j polynomials are already orthogonal. Also, we'll assume that each one of these polynomials, pk, is of degree k. And of course, for induction, you need a base case. I'll set p0 of x, so that's the constant, so we'll just set that equal to 1. So the idea is, if you already have orthogonal polynomials up to degree j minus 1, how do you get the next polynomial? So for that, we basically use Gram-Schmidt. So what I do is, I take my latest polynomial, pj minus 1, but that's of degree j minus 1. I need degree j. So I'm going to multiply it by x. So now this is degree j like I want, and then I take that and orthogonalize it against everything else. So I have the sum, where I use these inner products. So I have pi with x p j minus 1 all over pi times pi of x. Okay. All right, so this is like playing the role of my AJ. So it's one orthogonalizing against everything else. Now, here's where things become nicer in these, let's see, the orthogonal polynomial case, because each pk is orthogonal, and this is what I'm going to use a lot, orthogonal to all polynomials of lesser degree. Because the reason is, pk is orthogonal to p0, p1, etc. up to pk minus 1. And if you take any linear combination, it's going to be orthogonal to that too, because the inner product is linear. So here's how we can take advantage of that. If you look at this inner product right here, pi x pj minus 1. Now, what do we do to take the inner product? We multiply all of those together and integrate. Well, that means I can arrange these within my inner product any way I want, because multiplication being commutative and all that. So that's the same as if I take the x and move it over here. Okay. Now, this left operand is of degree I plus 1. And this has degree j minus 1. Well, this is, now I is already less than or equal to j minus 1. So this polynomial is orthogonal to all polynomials of lesser degree. Therefore, this is equal to 0 if I plus 1 is less than j minus 1. So in other words, I is less than j minus 2. Yeah, I guess it's familiar to some of you.
Yeah, it's a homework problem.
Okay.
685.
Yeah. So, okay. All right. Does everyone see that? It's just a matter of degree counting, and using this. So what's really convenient about this is all the terms of this sum go away, except for the last two. So in fact, I don't have to say I equals 0. I can say I is equal to j minus 2. So if the summation has at most 2 terms in it, I can describe this, each polynomial pj, depending on the previous 2. Okay. Oh, someone left something in my office. I'm gonna.
Are you not doing it?
What's like it's an extra time?
I was asking if she had done that. Will you shut up?
What?
It's not gonna
Leave the room for a second.
Yeah. There's some Schmidt talking in here.
Oh. Okay. All right. All right. So I can write pj as, well, to take it directly from this, x pj minus 1 minus p j minus 2 x p j minus 2 over p j minus 2 p j minus 2 times p j minus 2. Well, I'm saying p j minus 2 a lot. Okay. Minus, same thing with p, oh wait, that's minus 1. Okay. And then same thing except with j minus 1 instead of j minus 2. Okay, but now what I'm going to do is abbreviate this. Because first of all, I have 2 terms involving pj minus 1. So I can write it as x minus alpha j, pj minus 1, minus, and this is another constant, I'll call that beta j minus 1. Okay. Squared pj minus 2. Okay, where alpha j is defined to be just this constant. And then beta j squared is, now here I have beta j minus 1. Here I'm saying beta j. So I'm going to shift all these indices up by 1. So I have pj minus 1 x pj over pj minus 1 pj minus 1. Now, there's one sticking point here. This number here, I've given you no reason to believe that this is actually positive, so why would I call this squared? But I'm going to show you that it is positive. So for this, I can say, all right, so if I repeat the definition, pj minus 1 Okay, yeah. xpj over, now inserting the denominator is positive. It's just the numerator that we deal with. So I can play these same games with x. I can take x and move it over to here. Okay, now, if we look at where pj comes from, pj is equal to xpj minus 1, minus this other stuff. However, I can say, in this inner product, I can replace this part with just pj.
Wait, I got a question.
Yeah.
On BJ2, on the bottom, should that not be J minus 2?
Where?
The beta J.
Here?
Yeah. Should that not be minus?
Okay. Beta j minus 1 has pj minus 2. Yeah, that's why I give a warning. I'm shifting the indices.
Okay.
Yeah.
Okay.
Okay. Now, to justify the move I just made, now xpj minus 1 and pj are not the same. So why can I replace it in a product? The reason is pj is equal to this minus lower degree polynomials, to which pj's are orthogonal anyway. So that's why. So if I wrote out xpj minus 1 in full, I could write it as pj plus others, like plus these two terms. These are of lower degree than j, so the inner product of them is 0. So, and what do I have? This is the norm of pj squared over the norm of pj minus 1 squared, which is positive. So that's why I can call this something squared. Right. So now we have this very important relationship here. Pj of x is equal to all this. This is what is called a three-term recurrence relation. Okay. In other words, each new polynomial depends only on the previous two. So there's 3 polynomials in the recurrence relation altogether. So all families of orthogonal polynomials satisfy this. It's just a matter of what is your inner product that you're using. And that's determined by your interval and your weight function, both those things. Okay. All right. Now, so any questions about free term recurrence? How much time have I wasted? Okay. All right. Now, all of these alphas and these betas are defined for j greater than or equal to 1. However, I can also make this definition if I let beta 0 squared be defined to be inner product of p0 with itself. Because this doesn't apply when j equals 0. Then what I can do is I can define qj of x to be pj of x. So pj's are my orthogonal polynomials, and I can divide by beta 0 times beta 1 up to beta j. Then actually, okay, I think I have just enough board for this. Then I take the inner product of qj with itself. So that's going to be the inner product of pj with itself divided by all of these squared, because these betas appear at the denominator of this and this, so each one appears twice. Okay. Now, if I write out what all of these betas are in terms of these inner products, I'm going to have, well, beta 0, I said PJ up top. Okay, beta 0 squared is P0 of itself. Beta 1 squared, okay, so this is beta 1, this is beta j squared down here. So beta 1 squared is P1 over P0. Those cancel out. So this is beta naught squared, beta 1 squared, beta 2 squared is P2 over P1. So now the P1s cancel out. You can't see where this is going, right? So all the way down to the last one, beta j squared, which is PJ over PJ minus 1. So everything ends up canceling out except this PJ, which cancels with the 1 up top. In other words, everything cancels. So the inner product of QJ of itself is equal to 1. So when you have a set of orthogonal polynomials, which a PJ and QJ both are, but then the inner product of each one of itself is equal to 1, we call that what? Orthonormal. So these are orthonormal polynomials. Okay. So in fact, we can actually say that the P's and the Q's are normalized just in different ways. So the PJ, those are monic, meaning that the leading coefficient is equal to 1. Because we start out with P0 equal to 1, and then every time we generate a new one, we just multiply by x, which preserves the leading coefficient. Whereas the QJ are designed to satisfy the requirement that its 2 norm is equal to 1. So you always have something about these polynomials equal to 1, just different things. And sometimes the having a monic can be convenient for other purposes. Okay. And for solving least squares problems or Gaussian quadrature that we'll see in the next chapter, and you can use either form. Okay. All right, so any questions about the normalization? All right. Well, those of you who've had to look at this for other things like 685, hopefully seeing it done on the board helps cement it. So, well, we'll see. Okay, so now, so this actually applies for any inner product of functions that I could come up with that we could use this to define some family of orthogonal polynomials. So I'll just give a couple of examples of particularly important families of orthogonal polynomials. All right. So what I described which for whatever inner product you impose, okay, so integral from AB, F times G times the wave function. Okay. Now, certain examples, if the interval AB is -1 to 1, and your weight function is equal to 1, then the orthogonal polynomials that you get are called the Lagrange polynomials. And so their definition, use L for this. So first polynomial is 1, second polynomial turns out to be x, so that's convenient. And then the rest come from a three-term recurrence relation. So we have, and the coefficients work out pretty nicely. So one nice thing about the this recurrence relation, because in the general one I have x minus alpha j times the previous one. Well, x here we don't have anything like just x by itself times LJ of x, which means that the alphas are 0. But that doesn't happen in general, of course. And then. So another example, if AB is again minus 1 to 1, and the weight function is 1 over the square root of 1 minus x squared. Now the thing is, that's an interesting case because it's undefined at the endpoints, but having a singularity at the boundary is still okay, because at least the weight function itself is still integrable over the entire interval, because you integrate. What you get from the orthogonal polynomials are ones you've seen before, the Chebyshev polynomials. And that's where you have t0 is 1, t1 is again equal to x, and then this is a free term recurrence relation. Okay, so, and there are other well-known families of orthogonal polynomials that come up for various situations of like different intervals, like maybe 0 to infinity or something like that, and certain other weight functions. There are quite a few out there, like often referred to as like the classical families of orthogonal polynomials, but you just come up with any inner product with whatever interval, whatever weight function, you can get, at least you have a general procedure to get orthogonal polynomials for that inner product. Okay. What I have in the notes is like how you can use this free term recurrence, or just how you can generate orthogonal polynomials on the interval minus pi over 2 to pi over 2, just computing the necessary inner products. Well, actually, no, the example's not about that at all. So, I'm very carelessly reading my own notes. Okay, this example is important because it's about how you solve the actual least squares problem. I just want to see whatever things in particular from these notes I need to cover. Okay. Oh, right. All right, so I'll do an example of solving the least squares problem. So suppose we have a function, it's cosine x, on the interval minus pi over 2 to pi over 2. And I want to approximate this on this interval using Legendre polynomials, so inner product of a weight function of 1. However, I'm on the wrong intervals. Instead of because Legendre polynomials are from -1 to 1, I need to scale them to this interval. So if I write out the first 3 Legendre polynomials, so 1, x, and then the next one is, I have to go to the Wikipedia page for Legendre polynomials to look up whatever facts about them I need. Now those are orthogonal on -1 to 1, but I need polynomials that are orthogonal on this interval. So no problem. What I can do is just make a change a variable, or I can set. So I have x is equal to 2t over pi, where t is -pi/2 to pi/2. So that maps the interval -pi/2 to pi/2 to the interval -1 to 1. So what I get is L0 tilde of t, which is still 1. L1 tilde of t is 2t over pi. And then L2 tilde of t, I just replaced x with 2t over pi. So I get 12t squared over pi squared minus 1. Okay, so these are orthogonal of -pi/2 to pi/2 with my weight function equal to 1. So if your weight function is 1, you can always just take Legendre polynomials and shift and scale as needed on whatever interval you need. Okay, since the substitution, basically a u substitution to evaluate the integral, would not affect orthogonality. So what I'm going to do is I'm going to come up with a quadratic function that approximates cosine x. So f of x is approximated by, I'll call it f2 of x, which is equal to a constant, L0 tilde. So it's another constant times L1. Oh, I should use t instead of x. To avoid getting variables confused. C2, L2 tilde t. Okay. So I need to find these coefficients, C0, C1, C2. But since L0 tilde, L1 tilde, L2 tilde are all orthogonal, I have a simple formula for that. Each one is equal to inner product of f with that polynomial over the inner product of that orthogonal polynomial with itself. Okay. So now all I have to do is evaluate a whole bunch of integrals. So what I would get is, so for instance, f with L0 tilde is going to be integral -pi/2 to pi/2. Okay, that was weird. F, which is cosine, times the first polynomial, which is just 1. And you get 2 for that. And then, so we get pi/2, pi/2, 1 squared. So that's just equal to pi. So the coefficient, C0 is just equal, so C0 just turns out to be 2 over pi. So then I just compute the rest of these, and this is done on page 90 of the notes. So once we get all of the coefficients, so C1 turns out to be 0, and then C2 turns out to be something that we worked out exactly at least. Okay. So then, when I use all these coefficients to form my polynomial, so I have 2 over pi times 1 plus 10 over pi cubed, pi squared minus 12, times my L2 tilde, which is 1/2 12t squared over pi squared minus 1. So that's my approximation. And if I work out these as decimals, okay. Now, this is in contrast to, I don't have a picture of this somewhere. Oh, it's over here. Now I want to compare this to the Taylor polynomial of second degree. Well, that's a t, not an x. Which would be just 1 minus 1/2 t squared. Now, the Taylor polynomial is meant to approximate the function really well near its center, which is 0. This function polynomial is meant to approximate f as well as possible on the whole interval minus pi over 2 to pi over 2. This one doesn't care what happens that far away. So, so I have a picture on page 91. So I graph the two, and it's a pretty decent approximation. I mean, you have some error at the endpoints. In the interior, it hits it pretty well. But you know, it's only a second degree approximation. So if you want a more accurate approximation, you would use a higher degree polynomial. Okay. But you know, really all that's involved is computing these inner products.
Excuse me.
Yeah.
The interval minus pi to over to pi to is the right interval open or is closed?
Oh, closed. Oh, doesn't really matter, but yeah. Yeah. But yeah, what I meant to write there is closed. Okay. I have we got time? Oh, okay, we have about 20 minutes. Okay, so done. That's. I was trying to keep track of what I can throw away. Okay, did all that, Okay. Yep, that too. Okay.
Do you want to throw your notes away?
I recycle, yeah, but yeah. Unless I find mistakes in them during class, and then I have to, yeah. Okay. All right, now, okay, well, I'm in pretty good shape coverage-wise. I expected to not get through all these notes today anyway. Okay, does anyone want to ask any questions about the take-home?
Yeah.
Dang, okay.
Hey, yeah, you got the questions? I don't even print it out. Yeah. Which one would y'all prefer? 6, 7, 6, 8, or 111?
6, 7, 6, 8. But y'all, I mean, y'all do what you do.
111.
Yeah,
Yeah,
111, that's the one I
Oh,
want.
yeah, 111.
6, 7, 6, 8, and 111.
Do you want this
Okay.
Alright. This is
It's circled in blue,
Oh, 6, 8, 6, 7.
and then 111.
Do you have 111?
Yeah, these are different.
Oh, yeah, oh, here it is.
Okay.
Okay. All right, for 111. Okay, as far as zeroing in what is actually asked for. Okay. Because the first thing is actually asked, explain graphically or otherwise why either u little k equals u big K or b little k equals u big K for all iterations. When I say graphically or otherwise, just take it to mean graphically. So if you were to draw a graph on an interval AB of some function that just like a generic curve has constant concavity.
There's actually a graph in the book.
Oh, there is?
I haven't seen it. Yeah, if you scroll back up and it shows where it's the secant lines, if it's underneath the negative, then
Yeah.
u equals uk.
Yeah.
Positive, then opposite
Yeah,
or
there's a
something.
similar one in the book,
Yeah.
and I think you can use the same.
Now is that graph like for secant method itself?
Yes.
Okay, yeah,
Yes.
but you can adapt it.
Yeah.
So the key is, when you actually graphically carry out the iteration where it's going to be a slight change to secant method. Secant method just blindly uses the previous two iterates to construct a secant line, but you're going to use the last two iterates to exhibit a sign change. What you'll find is after doing a few iterations of this, that one of the points just never moves.
Is it somewhat like bisection?
Yeah, okay.
Okay.
Here's the intent of this method was to take a best of both worlds, a
That's
bisection,
what I thought. Secant.
a slow but reliable method like bisection, and a fast but unreliable method like secant method, where you get to reliability and not to speed. This actually is called a method of regular falsity or false position. And if you Google it, there are fixes to this method to try to perform the intended mission of having a method that converges rapidly and is also guaranteed to converge. But yeah, if you carry out graphically, you'll be able to get an idea as to why that is happening. Okay, now, as far as, I wouldn't necessarily say that one could simply deduce that the method converges linearly, just by eyeballing this, because you could show it's definitely going to converge, and you could make an argument that it's going to be linear because this is at least going to be as good as bisection, and bisection is linear. But it could also possible to prove, as you went to great lengths to do, that it converges linearly. Because it's a similar analysis as to what you would do for a secant method, except instead of working with xk and xk minus 1, one of your iterates is just going to stay stationary, and the other one is going to progress towards a root. Actually what you can do is to clean this off. What you can always do to show convergence, like if you think there's convergence to a certain order, and that's actually, this will give you two things at once. It'll prove that the order of convergence is what you think it is, and also give you what is asked for, the asymptotic rate of convergence, or the asymptotic error constant. As you look at the limits, as k goes to infinity, of xk plus 1 minus the root. Alright, so I should say this is to show linear convergence. That's convergence to some non-zero constant. If a constant was 0, that would mean superlinear convergence, like you would get from secant method. So the idea is try to work this out. And the key is when you look at xk plus 1, you would normally use a formula for the secant method. But instead of having xk and xk minus 1, you would have like xk and x capital K. Because one of those points isn't moving. And then you do error analysis similar to what's been done for other methods.
Oh, so your xk is going to keep moving, not your.
Right. Yeah, that's going to converge to the root. Yeah. Okay. If a book says, explain clearly what you mean by convergence of this method, just ignore that. Like,
What did it say?
explain clearly what you mean by convergence of this method.
Okay.
We're using the regular definition of convergence. Like, there's no point in discussing any other sense of it. Okay. And then you can discuss, advantages of the, if any, of the secant method. But okay. But yeah, this question has a bit of extra to it that kind of muddies the waters a little bit unnecessarily. Not sure why we do that, but yeah. Okay. Is it good with that one anyway? At least to try to proceed on it. Okay.
Yeah. So 6, 7 is 6, 8. Yeah.
Okay. Well, I'll pick one of these.
6, 7. Yeah.
Okay.
So 6, 8.
Oh, sorry. 6, 7, 6, 8 are very different. 6, 6, and 6, 7 are very similar.
Very similar, yeah.
Okay.
It's a homework problem.
Oh,
not
yeah.
a exam problem.
What?
6,
3,
7.
6, 7.
Okay.
Is that the one where you find the roots first?
No.
No, this
Oh,
is
that's
one where you
6A.
gotta find H, K,
Oh,
L, and L.
Oh.
Remember H, I, K, I, L, I, N, or L, 0, and L, N.
Yeah.
It's the same as
Oh yeah, I
6,
started
6.
that one where L9 and the LN are just the endpoints.
Okay. So 6, 7.
Yes.
I tried to do what you told me, but I think I got stuck.
Okay.
Yeah, I couldn't figure out what the key and the R is.
Okay. I will pick out. Okay, because you have to find L0, LN, HI, and KI. All right. I'm going to pick one of these to discuss to give you an idea. But the others, use some more ideas. Like HI. This tripling polynomial is of degree 2n minus 1. So we need, for each one of these, we need 2n conditions for it to satisfy, because each one's going to have 2n coefficients. So HI has to satisfy these conditions that HI of xj must be equal to the Kronecker delta, so it must be equal to 1 if I equals j, and 0 otherwise. But this is only for I equal to 1 up to n minus 1, because you only have h's that correspond to the interior points. So this is what makes it weird compared to Hermite, is that the boundary values and interior values, or interpolation points, are treated differently. That's why you have this L0 and Ln. So you have n plus 1 points altogether. So here we have n plus 1, okay, so j goes from 0 to n. So you have n roots specified, n plus 1 conditions altogether. But now, as for the derivatives, we have hi prime of xj must be 0, but this is true only for I and j equal 1 to n minus 1. So, because we do not care, so this is how this problem differs from Hermite. We do not care what the derivatives of any of these L's, H's, and K's are at the boundary points, because there's no conditions imposed there. Only the interior. So you have n plus 1 conditions here, n minus 1 conditions here for a grand total of 2n. Now, so hi has a double root at xj for j not equal to I. So that would suggest, also because you also want it to be equal to 1 at a certain point, you could try making use of of Lagrange polynomials, of course. But be careful which Lagrange polynomials. Like Lagrange polynomials for which points. Because, for instance, you want this to be equal, you want it has a double root at these guys, only for the interior points. It only has a single root on the boundary. So you can't just throw in Lagrange squared unless you want to unless you're going to adjust it, like cancel some factors out or something, and which you can do. If you have more linear factors than you need, you can always cancel out the ones you don't want. So that's something that can help you. Okay, so be sure, watch your notation. You might be using different Lagrange polynomials for different sets of points, like maybe all the points or just the interior. However you want to do it, just specify so I know what your polynomial looks like.
I don't know about the rest of y'all, but me and Brianna got that far. We got this, and we got Ki, which is basically the opposite. And then you find your Ln and your L0, which are just Ln for the 0 and then Ln for n.
Yeah.
I don't know how to find the equation. Like,
Okay. So, okay, for the rest of the problem, oh, you mean the error?
it's the same thing, but it's just for L is for 0, and then the Ln is just for the other point. Which you just do the x minus.
Yeah, L0 and Ln.
Are basically the same, except for one you plug in x0 and one you plug x in, just like you would for Lagrange, like x minus x naught, or x minus xn over x naught minus xn. But I don't know how to get the.
But you still do it.
Okay, so you're talking about how to get the error formula?
Like whenever we did the Hermite interpolation, like in class, you know how we did, it equals.
Okay, I was just saying how to get the formula.
Yeah, how we found Q and R, Qi of x and R I of x for the Hermite interpolation.
You mean H and K?
Well,
Yeah, but
I think-
I know what they're talking about. When you first.
Oh, for the remainder part.
Yeah.
Yeah, okay.
Yes.
All right. Well, I'm leading up to that, but I want to be careful
okay.
about how much I give away. Okay, so, but right here, we're only going to talk about the H's, and then you can try to adapt that to the other
Okay, that's
cases.
cool.
All right, so, okay, so, for instance, if I want to, I just have n minus 1 interior points. Here's what I can do. Now, this is not the only way to do this. It may not even be the simplest way, but I think it'll be the least messy. If I let L n minus 2 I x be the Lagrange polynomial only for the interior. So, because there are n minus 1 interior points, it has degree n minus 2, or n minus 2 roots. So, what I could do is if I start this off with this Lagrange polynomial squared, then that's going to cover a lot of my conditions. Like it's going to make sure that I have, it'll cover most of the zeros I need for the derivative, all but one. And it will cover equaling 0 at all the interior points except for xi itself, where it'll equal 1, which is also what I want. So this satisfies how many conditions? Well, this for the interior points, so n minus 1, and then n minus 2 conditions there. Okay, so 2n minus 3 conditions, because the degree of this is what?
Minus 2.
I square it though.
2n.
2n minus 4.
Yeah.
But that means there are 2n minus 3, so one more coefficients. So I have 2n minus 3 conditions. I have 3 conditions left. Also, I have, now I'm going to have this remainder, but yeah, now I remember what you're asking about. That, okay, and this has to have degree 3, and therefore it can satisfy 4 conditions. So what's left? I need it to be 0 at the boundary points. So that's 2 conditions right there. I need it to have a 0 derivative because I've satisfied all of these except one with just the Lagrange. And then the last thing is, okay, so, all right, so everything from a derivative is taken care of. Oh, all right. Wait, something's off here. 2n minus 4. Yeah, you have 2n conditions altogether. So, what?
Do we need 2n minus 4 or 2 minus 3 conditions? Right? We have 2n minus 3.
Okay, I need 2n conditions. Now, as far as, okay, so, yeah, because this takes care of all the interior points. So that's n minus 1 conditions. Then the 2 boundary points, so that's n plus 1 conditions. And then I have okay. So for a derivative, oh, well, yeah, because this is going to have a 0 derivative at all of the interior points except 1, for sure. Okay, this is thrown in. Okay. Oh, wait a minute. Yeah, there are only 3 conditions left.
That's what I was saying. We
yeah,
have degree
because-
2 minus 3 plus 3.
Yeah,
so
because
then-
this is degree 2n minus 4, but it says about 2n minus 3 conditions.
Yeah, okay. That's all I was like,
Okay, yeah. And I was like, I'm not missing anything. Okay, so, well, wait, if that's 2n minus 4, oh, degree 2. Yeah. Because this, oh, no, it's going to be, yeah. Yeah, it still has to be cubic to make the whole thing have degree 2n minus 1. It just said this is the only, as far as having a, oh, I know what the other condition would be. It is 4. Because this satisfies the condition that hi of xi equals 1. So in that case, it's covered, but this has to preserve it. So Ri of xi must be equal to 1.
so does that give us 2n plus 1 condition?
No. Basically,
Just the same.
these two combine
Okay.
together to satisfy this condition. Yeah, so basically you're trying not to mess things up.
Okay.
Okay. All right. Now, and since it's a cubic, well, what you can do though is these conditions, of course, are the easiest to satisfy. But you have to make sure that that's satisfied too. And you can always just proceed by integration. Okay. But at least these 2 conditions can help you to express it in factored form. And so you can cut down, like you express Ri as like partially factored So you know those two factors are going to be there, and then figure out the rest. To make sure that these other two conditions are satisfied. So, nothing to it.
Yeah, that's not nice. Oh, and only the derivative only needs to be 0 to xi.
Yeah. Yeah, just at that one point. Oh wow, we're past time. Dang. Okay. All right, so a little more orthogonal polynomials.